So coming to the next point is wide application across industries. So application of FEA in the different kind of industries. So you can say that FEA can be applied into the different industries. I would say that almost all the mechanical engineering industries FEA can be applied. So you can see that automotive industry, aerospace industry, civil infrastructure industry, energy and power, medical devices, consumer products, marine and shipbuilding, industrial machinery. So I'll come to the first point is automotive industry. So how FE is going to be used in automotive industry? So like in automotive industry, yeah, you need to check the strength of the parts. So the sheet metal parts, the BIW parts, how much the load is acting on the BIW, the crash test is there in the vehicle. So in different software like LS Dyna, they do the crash test for the vehicle. So in that case, they discretize everything into a small elements, and they apply load at all the crash vehicles, and they check how the vehicle is going to be perform and how the impact is going to travel, whether it will travel to the driver or passengers. So that kind of thing they can check in by using FEA. You can check a different part like suspension parts, BIW component, engine components, chassis. So all kind of different kind of mechanical things which are in there in the automobile, where you can apply the loads, boundary conditions, stresses, heat, vibration, everything that you can simulate using the FEA in automotive industry. Then in just I showed you in the aerospace industry, so where you can check the aircraft structures, landing gears, wings, and other linkages into the aircraft. There you can see check by using the finite element analysis, or whether in the rockets, the vibrations, the engine performance in the jet engines. You can check the temperature distribution across the blades, or in the rocket engine, you can check whether the combustion chamber going to be melted or not. So all these kind of things, the 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 temperature distribution in the engines, that in the jet engines or in the rocket engines, or even other kind of engines, you can check by using the FEA. So in the aerospace industry, the FEA can also be used. So next, one of the most important applications is in the civil and in infrastructure, where you can check the whether bridges are going to be fall or not, how the bridges will behave. We have how the towers or different structures is going to behave uh, with the help of static structural analysis or non-linear structural analysis. I will come to that point in the future videos. So I will explain what non-linear structural analysis, linear structural analysis. So these kind of things. So you can check whether the structure is going to fail or not. So how it is going to behave with the different vibrations, frequencies, resonance. So that kind of thing we can simulate using the finite element analysis. The next thing is energy and power. So in energy and power, you have turbines, pressure vessels, pipelines, nuclear components. So imagine like the turbine. So how the fluid is going to affect the turbine blades, how much stresses is going to be generated into the turbine blades, whether turbine blades can sustain that kind of a shock, fluid shock, or resonance or vibrations coming from the air or from the fluids. That kind of thing you can check in the pressure vessel like boilers. Either you can check whether that boilers or pressure vessel can sustain that amount of pressure or not. In the pipelines or nuclear components, so the nuclear components, whether in nuclear reactor, you can check that whether these insulating component, whether they can stand that much heat or pressure, uh, kind of things, it can sustain or not. The pipelines, whether these the pipelines in the boilers or in power plant, whether these pipelines uh, can sustain for the longer amount of heat, whether they get uh, going to be failed or not. So these kind of things you can checking the energy and power sector, whether medical devices like implant, prosthetic, surgical tools for the long. So prosthetics like whether any kind of a part we have designed for any kind of a knee or joints in the longer term, whether that part is or whether that joint can behave or it's going to be failed or not, that we can check uh, in the medical devices. So the medical devices uh, is very what you can say that very important industry or where we need to think a lot about sustainability, uh, then uh, how the patient is going to behave, his health conditions. So in that cases, we need to be very precise in our boundary conditions, loading conditions, or we never any of the engineering assumptions. So that is where the finite element can also be used. The consumer product, as you can know, the washing machines, furnitures, sports. So you can see that in the sports like skating or skateboard. So whether the kids or sports player, whether they are using these kind of suppose like a small kid who is playing the skateboard and he is not just using for his skating, whether he might sit on that skateboard. So for that we need to consider how the material should be taken to design the skateboard, how different load out of box thinking there's to be we need to consider. So like maybe you can see the furniture. So people just not sit on the table chairs. They might sit on the tables also while some friendly conversation or anything. So we also need to check whether that furniture is going to be failed or not. So these kind of different consumer products we need to check for the like you can say um, washing machine or a fridge or some sport equipment. Um, so those kind of things we have to analyze in the in consumer product. So next point is marine and shipbuilding. So whether ships can can be survived in very cold water. So there is a phenomenon that sometimes in much of the cold water the material behave differently. So there is a one case of Titanic failure. So many things, so many people know that Titanic uh, was uh, was saying because of it collided with uh, ice uh, iceberg. So so because of too much cold condition, the material, the steel is behave differently. So then we have to consider we have to give the different material properties to the steel. So isotropic or anisotropic material properties we have to give to the components, and then we have to check whether the material or a component, how that component is going to behave. So that kind of things we have to consider in the shipbuilding or submarine design. In submarines, usually dive very deep, like 150 meters, kind of thing. So then that time the pressure is coming on or from the all side of the submarine. So at that time, the submarine needs to sustain. So different submarines and different submarines were designed for the different atmosphere. Like suppose a Soviet class or Russian submarines need to survive in very cold water because Russia is in Arctic. So it need to survive. Their submarines needs to survive in very cold waters. The submarines are almost 24 hours. Uh, yeah, is in water. So the material, how the material is going to behave, and how that suppose the material properties are changing, and how the loading conditions will change for the very cold water conditions. So then in the Indian Oceans, in India or some tropical countries, the sea water is or ocean water is very warm. So then that time the submarine material should be a different. It should not be a Russian class material. It should have some different material properties. It should the material is going to be behave differently. So then that kind of for that kind of conditions, the loading conditions and how the load or the crack propagation will happen inside the submarine, that we have to study. So in that case also we need to use the FEA how for the different material, and for the different material how the structure is going to behave, how material is going to behave, how the crack propagation inside the material will happen. So that kind of things we need to consider. uh, so yeah, so finite element can also be used in marine and shipbuilding. So then last one is industrial machinery. So in gears, machine tools, then robotic arms. So how these arms are going to behave. So if they are continuously they are continuously working and sustained kind of loading conditions are there. So gears, you can see that in automotive gears or transmission gears, the gears are continuously changing. There's a different kind of loads, uh, and then different kind of speed ratios are continuously acting on the gear. So that then that kind of environment, so gear has to sustain these kind of different forces, different RPMs. So that kind of thing we need to check. Then how the gear material and how the gear tips going to be stressed, or how the load is going to behave on that gear tips we need to study. So in that case also we need a finite element analysis. So then I'll come to the next point is the FEA process. So how the finite element analysis is going to be done. So there is a step-by-step process in the finite element analysis. So I'll explain that step-by-step process. Then the first process is pre-processing. Pre-processing means create a CAD model, define material properties, assign loads and boundary condition. So in pre-processing means it shows in the word what pre-processing means. The pre-processing means you can create a CAD model. You create a CAD model. You applied a material to it. You apply material to it, and then you apply load to it. So this setup is known as a pre-processing in simple language. So this setup is known as pre-processing. So then next step is meshing. So what we do, we discretize the model into finite element and nodes. So what we do, so when we apply the load will transfer to the different part of the body. So then we need to calculate how the loads and stresses are going to be generated into the different part of the body. So suppose if I take a small plate, hole in it, and suppose if I apply the load to the plate, so the stresses will generate over this region, and then stresses will dissipate on this as we go away from the hole, the stresses is going to be dissipated. So there will be no more stresses at the end of this plate over here and over here. So then we have to check how these stresses and how the stress is going to be dissipated. So these kind of calculations we need to do in FEA. But how they can be done? So then first we need to divide the plate into a small element, and then this element will carry all the stresses and displacement, and one element shift its displacement to the other element, then other element shift the displacement to the next element. Then that's how the stress is going to be distributed. So that's why the meshing part is very important. So which kind of mesh you are going to use? So I will tell you the what kind of a different kind of a mesh are there. Linear 1D element, 2D element, 3D element, all these kind of element and their meshing I will discuss into the future for the meshing conference. Then the solver. The solver solves the equations. So solver is the governing equation to find out the unknown displacement and other results. So what do you mean by the governing equation? What do you mean by the stiffness matrix? So these kind of things I will explain. So once you load the apply, once you apply the load, the computer or software calculates the load and its equations, its formulas, which are coding at the back end of the software. It will calculate the load at each element and each node, and it will create a stiffness matrix and it will show the result. So this kind of process comes into the solver. So then next is pre-processing, post-processing. The post-processing is a thing is to visualize and evaluate result. So then the software will give us the result. So how the stresses are going to be there in the part. So you can see that here in this image, you can see that red means high stresses, blue means low stresses. So the software will show where the stresses are going to be generated. Okay. So you can see that here in the images stresses are more over here and the stresses are less in this blue region and more in the red region. So similarly strain it the software will show where the more strain or more displacement is there. So similarly the temperature distribution. So this kind of results software will show us. Then we have to interpret how these stresses are going to be there, how it will behave. So sometimes we give the wrong boundary condition and wrong stresses are generated at the wrong end. So in that time, we have to be very important at the start of the FEA. So in the pre-processing, once the pre-processing is going to be, suppose if you made a mistake in the pre-processing, then your entire analysis is going to be wrong. So that's why we need to go step by step and check each and every step accurately and thoroughly whether we are creating the CAD model and the pre-processing and defining the boundary condition or material condition that we need to check properly. So these kind of steps are in the FEA. So you can say that these steps can be divided into the four types. So this is the basic introduction of the FEA. So coming to the next point and the last point is types of analysis. So you cannot just do a one or two kind of analysis in FEA. So we can do the multiple kind of analysis. I just showed you the structural analysis where we can uh, apply the loads to the bridges, to aircraft wings, to automotive components. So this comes under the structural analysis. Another is the thermal analysis. You can apply the heat or steady state heat or transient conditions. Then you can apply the heat and you can check how the part is going to behave under these thermal conditions. Then third is the modal analysis. Modal analysis means you can apply the different frequencies and how the component is going to be behave. So this comes under the modal analysis. Then buckling analysis. So buckling analysis is how your part is going to buckle in different loading conditions. You can predict whether that part can get buckled or not. So that also comes under the buckling analysis. Then fatigue analysis. So you can apply the load on the component for a very long time and with fluctuating load. So suppose like in your automobile, maybe in sometimes in your suspension, imagine that your suspension uh, you are applying the load in the suspension. So sometimes in your car, two passengers are going to be seated, or only one passenger is there. So so there will not be any fixed number of passengers in your car or in your bus or in your vehicle. So that kind of in that way, the different loads are going to be applied on your suspension spring or suspension component and your loads and that these loads is not just for 2 minutes or 3 minutes. So suppose this loads is acting in for a very long time, like 3 hour, 10 hour, 8 hours, okay, and for even not just for 3 hour or 10 hour. So these 3 hour, 10 hour, 8 hour loads is going to be there for the whole vehicle life. So maybe your vehicle life is maybe 10 year or 15 years. So imagine your every day your vehicle is uh, having a load of 3 people or 5 people for next 3 hours or 4 hours. So some days maybe two peoples are there. Some day maybe only driver is there. only for 8 hours. So there are different loading conditions. So then how your part is going to be behave in that condition. So it comes under the fatigue analysis. So we have SN curves in fatigue analysis. So yeah, I will explain you what is SN curves in fatigue analysis. So this kind of analysis we can do the in FE. So then next is acoustics. So vibrations, how your part is going to be behaved in different vibration or sound. So whether that part is going to be sustaining that sound or vibrations that you can check. Then fluid structuring interaction. So that is also we can perform in the FE. So these kind of different things we can perform in the FE and all the different industries. So it's a vast domain. So a very interesting domain. So yeah, we will going to see one by one uh, what is FEA. So there are how engineering was before the FEA. So here the spelling mistake is there. So I will explain how the engineering before the FEA was invented, how they do the engineering. So I will explain that in the future videos. Then a complete index, you can see that we are going to see different topics in FEA. We have just seen introduction to the FEA, but in future we are going to see what is FEA, why use FEA, basic concepts in FEA. So what are the elements in finite element analysis in FEA? What is meant by node? What is meshing? What is degree of freedom? What is material property? How the loads are going to be applied? How the boundary conditions needs to be taken. So what are the different contexts in FEA? So what is the element stiffness matrix? What is the global stiffness equation or the global stiffness matrix? Why the displacement is for solve first? Why the displacement approach there is there in the FEA? So what is the shape function? What is pre-processing? I just explained the what is pre-processing, but I will explain into the detail what is pre-processing, then solution stage. So how solutions need to be obtained and what to do with this solution, how to interpret results from these solutions and post-processing. So the type of analysis I just explained you the types of analysis. So different type of analysis like linear analysis and non-linear analysis.